All right, everyone. So, good evening, and thank you for tuning in. I really appreciate this opportunity to hold this kind of webinar. And actually, this is the first time I hold an online webinar, and I'm excited. I'm looking forward to share with you guys a little bit about what I've learned, what I've researched recently. So, first off, I would like to introduce myself to anyone who doesn't know me. My name is Meng Ma, and I'm a postgraduate student at EBS University in Germany. Currently, I'm studying automotive management, and my previous internship experience has been ranging from working as automotive consultant at Roland Berger to, I spent my past summer at Adam AG here in Hüsselsheim, Germany. I really got a wide range of interest in terms of automotive industry. So it's especially for those things related with the technology, related with tech stuff, digital transformation, things like self-driving car, and which I'll talk about in the next few minutes, and also car sharing, future mobility, something like that. These are really, what I wanted to learn more about and dive deep into it. Yeah, so in this webinar, actually, I plan to make at least five webinar in this self-driving car webinar series, and yeah, this will be the first episode, and yeah, I would like to really focus on self-driving car, and because as I said, this is the what I'm really interested, and really the point to hold this kind of webinar series is to motivate myself to learn more about technology, the business model, the what's going on in this industry, and kind of everything around the self-driving car, because this is really I would say fast evolving industry. If you really follow closely and check the news every day, you will see that there are new stories, new technologies, the innovation, and the collaboration between different players. These kind of news coming out every day, every moment. That's very, so crazy. And yeah, in this first episode, I would like to, actually not talk about the current news. I like to date back to the beginning of the self-driving car in the past decades, and yeah, just talk to you guys something about the DARPA Urban Challenge in 2007. I will try to break down the architecture of some of those self-driving racing vehicles in that challenge, and just give you a brief idea how those self-driving racing vehicle work, how those system architecture look like, and also introduce some basic technology or algorithm widely used in that challenge, and also some novel features originated from that race. Cool. Uh, so yeah, just give you an overview about what I'm going to talk about in this webinar. So first, I will just quickly go over the 2007 Urban Challenge, and then I will dive deep into three of the racing vehicles, which are Talos from MIT, Boss from Carnegie Mellon University, and a Junior from Stanford University. And at the end, I will do a brief summary and comparison to just summarize some of the similarities among these three vehicles, as well as some novel features for each of them. Okay, so that's it. Now I'm gonna start right now. Uh, Actually, before 2007 DARPA Urban Challenge, there were two Grand Challenge competitions which were held in 2004 and 2005. The task for the Grand Challenge was, I would say, simpler because vehicles were just required to travel from point A to point B, and also avoid some obstacles in that period. So, but really the challenging part is the environment, because the Grand Challenge was held in the desert. So finding and navigating the road and the trails in the desert was definitely not an easy task to accomplish. I think the first Grand Challenge was, I would say, disaster because no team traveled more than 7.4 miles. So many teams drove 0 mile. They just couldn't move at all. And also, you can see on the picture that a guy called Anthony Lewandowski. I think he is currently work at Auto, which is a self-driving truck company acquired by Uber recently. And this guy, he developed a self-driving motorcycle in that event just for fun. I think you can see that people was just go crazy at all. They you know you can imagine that making a self-driving car is difficult enough, and how about making a self-driving motorcycle? That's so crazy. And actually, there was no winner in the first Grand Challenge because no team traveled more than 7.4 miles, as I said. So then the DARPA decided to hold another challenge in the next year, and it turned out to be a huge success. And you can really see the improvement. There were 5 teams complete the race, right? And yeah, the winner was Stanley from Stanford. You can see on the picture, it's the Stanley and their team leader, Sebastian Through. And after Stanley was followed by 2 racing vehicles from Carnegie Mellon University. So this was really interesting. You can really feel that these 2 universities kind of have some rivalry between them. Actually, the guy on the picture, Sebastian Thrun, he was previously a faculty member at Carnegie Mellon University, and and he also participated in the DARPA Grand Challenge 2004 as a team member in CMU team, and but in the next year DARPA Grand Challenge he came to Stanford and led the team Stanford and win that team. So Sebastian just was kind of really proved himself by this race, by this DARPA Grand Challenge 2005. And later on, you will find that actually the survival story even continued in 2007 Urban Challenge when the boss from CMU finished first and beat the junior from Stanford. So the cool thing is after the 2007 Urban Challenge, Sebastian Thrum and the team leader from Boss, the guy Chris Urmson, they came together to work at Google for Google X project initially, and then the Google self-driving car project. And then and now they both left Google. Sebastian actually founded the online educational platform called Udacity, where he is going to launch the very first self-driving car online course. And I believe it will start from the end of this year. Oh, I'm super excited about this news, this online course, this online program. And yeah, I totally believe that they can make their own self-driving car at the end of the course. So no doubt about it. And Chris Urmson, he left Google a couple of months ago, and I'm not sure where he will head in next, but definitely, there are a lot of companies like Uber, or those incumbent OEMs. They are really eager to have this kind of talented people in this area working for them. And yeah, let's talk about the 2007 Urban Challenge. So here are some numbers about this racing. Initially, there were 89 teams registered for the competition, and 53 were qualified for DARPA site visit. And then 35 teams were selected to compete in the so-called national qualification event. And finally, only 11 teams were made to the final competition. So, DARPA didn't want too many teams participating in the finals due to the safety reasons, so they just keep it in 11. I think the result was quite good. 5 of 11 teams were eliminated during the first mission in the final, and the rest 6 all finished the course. Boss, the vehicle called Boss from Carnegie Mellon University ended up with the first place and followed by Junior from Stanford. Yeah, you can see the rivalry again, right? And Virginia Tech, they finished with their third place, and the Talos from MIT ended up with fourth. So I think for me, 2007 Urban Challenge is more interesting and more worthwhile to learn, and because this is the first time that self-driving car technology was implemented into the urban environment. And yeah, the vehicles need to obey the rules in the urban traffic. They need to recognize the stop sign. They need to recognize the traffic light. They also need to deal with a lot more complicated circumstances, right? Such as how to handle the intersection, how to do the overtaking maneuver. Really, there are a lot of interaction between vehicles. Also, the focus point was really shifting from the hardware part in the DARPA Grand Challenge to the software part, to the algorithm in this urban challenge. And the teams are focusing on how to make timely decision for vehicles, how to let vehicles handle those complex situations. So that's also the difference between the previous two Grand Challenge and the 2007 Urban Challenge. All right. So in the next three parts, we'll go deep into those three racing vehicles. So let's start with the Talos from MIT. So here you can see this is the high-level view of the system architecture of Talos. On the left top corner, there are two inputs, MDF and RNDF, which are mission data file and map file provided by DARPA. So with these two files, Talos can roughly figure out where it was and where it needs to go. So then you can see one of the important parts is the perception in the middle. So the perception subsystem let Talos to figure out how the environments around it look like. So where are the obstacles, where are the hazards, especially those curbs, where are the fast vehicles, and where are the lanes. But to achieve these perception tasks, the key issue is to process all the data from multiple sensors first. So here you can see we have the cameras, we have short range radars, we have long range radars, we have 6 planar LiDAR, we have Velodyne 3D LiDARs. So all these sensors, we need to do the sensor fusion or data fusion more precisely before we can do the perception tasks. And after we kind of understand where are we and what's the environment around us and where we are about to go, so the next question should be how we can manage to go to the place we want to go. And that's about planning and control, right? We have navigator. They also create a drivability map to support the motion planning. So the ultimate goal is to find out a path that the vehicle can follow to reach the goal. Of course, you need to obey the rules and you need to avoid collision with obstacle and other vehicles. That's the baseline. So at the end, all these data should be sent to the brake, to the gas or steering system on the vehicle. So then I would like to pick up some of those subsystems and have a detailed look into them. So first I would like to talk about the obstacle detection and tracking subsystem. Let's zoom into it. Here you can see that actually it could also be further decouped into two independent subsystems. One is the left part using LiDAR data inputs, both planar LiDAR and Velodyne LiDAR, and the other is the using radar data inputs. So here I just focus on the LiDAR-based part. So actually the main idea behind the LiDAR-based obstacle detection and tracking system is to cluster those points clouds and group them together, group those those are corresponded to the same objects together, and then to check them over time to distinguish whether it's a stationary object or a moving object, right? So to do so, first need to use a so-called front-end module to classify the LiDAR output into three categories, which are ground, outlier, and obstacles. So you can see for the planar LiDAR front end, we really need the redundancy. By redundancy, I mean we need multiple sensors. We need multiple planar LiDARs so that we can differentiate obstacle from the other stuff. You can see on the picture that if we just have a single planar LiDAR, we cannot distinguish static obstacles from hilly terrain. And however, with the multiple planar LiDARs, we can differentiate them based on the measure of based on the measure of change of the c axis, so we can solve this problem. And same with the planar LiDAR, we also need to do the classification for the Velodyne LiDAR, right? But here it is more complex. Actually, you can see on the left picture, they use a so-called ground estimation algorithm, which can generate ground candidate points by dividing the area ground around the vehicle into a polar grid. And actually, they predetermine a threshold of 30 returns as a prediction standard for a ground candidate point. So you can see due to the noise in the Velodyne, the lowest 20% of the points that it was below this blue plane will be rejected as potential outliers. This is kind of different from the planar LiDAR because there is not so much outlier returns in the planar LiDAR data. So then to really figure out a grand model, as you can see in the right picture, they use a maximum slope constraint, and then they linearly interpolate these ground candidates in, so that's the blue curve, so that they can build a ground model. The next step, so we need to remember that our ultimate goal is to cluster these point clouds together and then track them over time. So, but there is still some problem before we can further use our algorithm to do the clustering and the tracking. So the first problem is that there is still large amount of point clouds even after the front end process. And the second problem is that because we use the planar LiDAR front end and also the Velodyne 3D LiDAR front end, so the data fusion is necessary in this circumstance. So here, what they do is they further reduce the data by creating a notion of chunks. So by the definition, a chunk is nothing other than multiple spatially close range samples. So that means they do the data reduction one more time after the front end process. All right, so now that we have the chunks, we have those chunks, we are fine. We can do the clustering and tracking with those chunks. So how can we clustering those chunks into groups? They determine a threshold that any two chunks within 25 centimeters of one another will be grouped together and regarded as the same physical object. So that's the meaning of spatial clustering, right? There is threshold of 25 centimeters in space. In terms of temporal association, here we have the data of, for example, the group A, the object A, for the time t, and at time t plus 1, we'll also generate the data for group A. So what we need to do is to associate these two group of data together and compare the bounding box of these two to yield a velocity estimate. So what we not only need to distinguish whether it's static or moving obstacle, we also need to know roughly estimate the velocity of the object if it is moving. So that's the point. That's the idea behind the temporal association. However, I think there is the weakness for this system is that it really has some trouble estimating the velocity of slow moving obstacle. You can see actually I believe that there is an accident between MIT and Cornell. So the reason one of the reasons they found out is that uh, Cornell's vehicle was moving really slow by that time. It's actually slower than 3 meters per second. So and this actually happens to be the threshold for Talos system to distinguish whether it's a static object and a moving object. So Talos just treats Cornell's vehicle as static objects and try to try to do the overtaking maneuver, and then they just collide. It's really interesting. And the next subsystem I would like to talk a little bit about is the lane detection and tracking. So here you can see in the overall architecture, the lane detection and tracking, the output of lane detection and tracking uh, will be sent to the navigator and the drivability map. So this is really essential for the later planning and control of the system. So basically, it's a three-stage process, I would say. The first stage is to detect and localize the painted road marks in each video frame with the help of multiple cameras. They use the cameras to do the road paint detection. And they use a filter that runs on the image, basically searching for the change of pixel intensity. So you can see that the filtered image that the road paint, the road mark is like evolving as you drive on the road. Then in the second stage, the system constructs a center-line evidence image using the LiDAR-based curve detection and road paint detection that have been done in the previous process. And most 5 lane center lines, you can see here, that's the blue curve, are identified by fitting parabolic segments into the ridges of the image. So finally, the third stage is lane tracking. So we hope that our system can maintain a stable estimation of the nearby lanes as we travel along the road from time to time. So to do that, we first need to use the RNDF map data provided by DARPA. So it can be treated as a prior to give the system some kinds of information about the number and the type of the lanes. However, the RNDF file, it's really perform not very good regarding the position and the geometry of the lanes. So that's why we also need a lane centerline candidates derived from the previous 2 stages. So these 2 parts of data should be fused and updated in real time to achieve this kind of closed loop lane tracking. So that means that the map data might say that. So here here you can see on the picture that the map data might say it is a straight line, but as you drive along the road, you will see actually it is not a straight line segment. Actually, it's a curve, and this closed loop lane tracking system can really estimate that and reduce the error. So now we know where is our vehicle, where are the obstacles and other vehicles around us. We've also estimated the lanes and the roads we are about to go. So the next question is how can we manage to go there, and how do we plan to reach the target place? So that's a task for planning and controlling. So here you can see for the navigator system in the planning and controlling. Navigator, it actually plays the role of mission planning, the high-level mission planning, and it's responsible for planning the high-level behavior of the vehicles, which includes the passing, the intersection, precedence, crossing, and merging, also the generation of the goal for the motion planner, turn signaling, something like that. And so next one is the so-called drivability map. So there are a lot of perception data in it, and you can see that consists of a lot of regions. One of them is here. You can see there is an infeasible region. It is, for instance, there might be an obstacle, or this region is not the place we want to go. So we call it infeasible region. The second one is high cost region, which should be avoided if possible. So, but it is also accessible to the vehicles in case you really have no better path to go. You can drive into these high cost region, but it should be avoided if possible. And also we have the restricted region on the drivability map. It is defined as the region that may only be entered if the vehicle can stop in an unrestricted area further ahead. So what does that mean? I think we can just put it into this way. If there is other vehicles block the lane, or there is a traffic jam ahead, so in these circumstances, the Talos will not enter this restricted region because there is no unrestricted place to go further ahead. So the Talos will wait in the current area and keep a safety distance so that later on maybe it can do an overtaking maneuver or have enough space to turn around, something like that. So yeah, like I said, the navigator tells I'll go and send it to the motion planner, and we also have the drivability map on hand. The data from the drivability map will also be sent to the motion planner. So now we can use this motion planner to find for ourselves a feasible path, which is the path that our vehicle can drive, and of course doesn't collide with other obstacles and vehicles. And also, we could not go off the road. So, and later on, this feasible path will be sent to the controller, and together with the speed command and the other steering command, so you can see that's the role of the motion planner in the whole planning. So here the approach they use to do the motion planning is based on a method called rapidly exploring random tree. So here you can see our vehicle is on the left side and we want to go to the blue dot. That's our goal generated by the navigator. So like I said before, now we need to find out a feasible path that help us reach that goal. So the way they do that is sampling points, sampling those motion control points, they call it. Let's say here we sample the first point. So if we want to go there, we need to follow this predict path. And this predict path is translated directly from the motion control point, but it's not the linear line in orange, because the vehicle needs to turn arbitrarily and then follow the red curve. So the next step would be, let's check whether this path is drivable or not. So we need to compare this path regarding the drivability map. As you can see, actually in these circumstances, this path will bring us to the infeasible region because actually you drive off the road, right? So let's repeat the process and sample another point. So in this case, it crosses the center line, and yeah, again another point, also the same situation across the center line. So it's also you might say it might not be the infeasible region, but rather the high cost region. That means we should try to avoid it if possible. So if because we cross the center line, and if there is no better path, maybe we can try this path. So here we sample another one. All right, and that's too bad we collided with the obstacle. So it's also infeasible path. And yeah, finally we sample a point which is safe, and from this point we can sample another one. So just like the name indicates, it's it's a rapidly it's like a tree, rapidly explores the environment, and just so we just keep repeating this process until we can find out the path to reach the target, to reach the goal. So here the red curve turned out to be the feasible path. All right, so that's the basic idea of this RT-based motion planning process. And yeah, another important thing is that at the beginning, we sample the input to the controller, and later on, we also sent the output, the feasible path, and the speed command, the steering command back to the controller. So that means actually it's a closed loop system. The motion planner and the controller, it's in a big closed loop system. And the major advantage is that this system is able to construct more stable trajectories as the environment changes because it's closed loop. Cool. So now let's move on to the second racing vehicle, which is also the winner in that DARPA Urban Challenge. That's the boss from. So here you can see there are actually four major components under the overall software architecture for BOSS. These four components are perception, mission planning, behavioral executive, and motion planning. Actually, I would say it's quite similar to the architecture of Talos, right? We need to first perceive the environment around us and then do the planning and controlling. So then let's just break it down and go through the perception and the behavioral executive parts. These two parts I think is most interesting. So first of all, to perceive the world and to really understand the environment around us, we need multiple sensors. So to measure the environment and then provide us with the data, right? So here again, you can see that the vehicle bus was equipped with 5 continental radar. 2 of them are long-range radar, 3 of them are short-range radar. Also 2 Conti fixed-beam laser scanner, and 6 lidar, and 2 EBO lidar, and also 1 Velodyne 3D lidar. So yeah, you can see that really the novel sensor, which kind of used by almost every team, is this Velodyne 64. You can see in the table that it was the only sensor providing a very wide vertical angle to kind of give you detailed and reliable 3D information about the obstacles. So I would say that DARPA 2007 Urban Challenge was really the very beginning of the application of 3D LiDAR on the self-driving vehicle. And if you fast forward to today, actually you find it that we have a lot of 3D LiDAR products, and there is also clearly a trend that that the LiDAR become smaller and smaller. The price is going down, and a lot of manufacturers also develop the solid LiDAR to the kind of the second generation to replace the first generation mechanical LiDAR, the rotary one. And really, the LiDAR is becoming the go-to sensor for developing a self-driving vehicle. You can see those products from Velodyne, the new Puck LiDAR, the S3 from Quantigy, and also the solid state LiDAR chip, which is developed by MIT and DARPA. So these are really, the technology is evolving so fast, and this area is this LiDAR industry is so dynamic, and there are a lot of investment, acquisition, and the new technology come up every day. It's just just evolving together with the self-driving industry. These two industry are really dynamic and amazing. Okay, so here you can also see is an illustration of the mounting location of all these sensors on the vehicle. So really the key issue is to provide a redundant coverage, and you know that different type of sensor, they can complement the detection features from each other, right? So here we zoom into the detail subsystem, into the perception subsystem, and you can see that it could be further divided into three subsystems. The first one is road estimation, and the second one is tracking, and the third one is static obstacle estimation. So in the road estimation subsystem, they develop a road shape estimation algorithm, and then combine it with the map database. That's the RNDF file provided by DARPA, so that we can create a very specific road structure model, which contains the information of intersection, the different zones like parking lots, and also the road lanes with the information of width, direction, curvature, and so on and so forth. So yeah, using this row structure, we can uh, we can do the rest of the work of the perception, that is to detect the obstacle, and also at the same time, as we mentioned in the previous case in Talos, we need to also check those obstacles over time, so that we can distinguish whether they are static obstacles or dynamic obstacles. So here you can see the output of this tracking subsystem is to create a dynamic obstacle hypothesis list, and which will be further sent into a dynamic obstacle removal in the static obstacle estimation subsystem, and finally we'll get a static obstacle map. So this will be further used to do the mapping and the localization. So actually, I would like to go deep into the tracking system, and you can see here the tracking subsystem actually has a two-layer architecture. So every time a sensor generates a new data, its corresponding sensor layer instance first will request a prediction of the current set of dynamic obstacle hypotheses from the fusion layer. And now we have a predicted obstacle hypothesis, but we have no clue whether it is moving or not, or maybe it could be a noise. So we need to eliminate it. So what we need to do further is to extract the features of our observation, and run a two-way validation. Hereby, features, I mean, it depends on it depends on the type of sensors. For instance, if you use the planar laser scanner, you use the planar LiDAR, so it will use a box model to interpret the obstacles. So the features of this box model could be those edges of the box. So, but what if you use the radar, so which is supported by a point model, so the features are those point targets, so they are different. And after the features have been validated by the local feature validation in the sensor layer, you can see, and also the global feature validation in the fusion layer. So that's why I call it two-way validation. And the next step is to do the data association. In to do the data association, and the validated features will be sent back to the sensor layer. And as you can see, uh, by this time, the data measurements will be generated into the dynamic obstacle hypothesis list. So that's the whole process in this two-layer tracking subsystem. And now let's go back to the overall architecture. You can see that the right-hand side is the planning and control part, right? There are three components. Two of them also exist in Talos system, but in both system, it's kind of split. Some of the behavioral management tasks from mission planning. So it has a more specific subsystem, which is called behavioral executive. So the target of behavioral executives to generate a series of incremental motion goals for the motion planning subsystem. And here the motion goal, for example, it could be in the case of driving in the parking lot, it could be maneuver to a particular parking spot, or in the case of driving along the road, the motion goal could be drive to the end of the current lane. And yeah, together with those motion targets, the system will also generate some motion parameters to control the behavior. So in most of the case, one of the motion parameter is the speed command, and the other one is the lane tracking. So let's say we need to let's say we need to, for example, we need to reduce some speed to keep a safety distance, or we should accelerate a little bit in order to fulfill a safe passing maneuver. So that's what motion parameter controls. So here you can see in this zoom in illustration that there are mainly three functional contexts in the behavioral executive subsystem. And yeah, the first one is the goal selection, and then we have the intersection handling and lane driving. So here you can see in the part of goal selection, the state estimator first use the vehicle's geometric position to determine vehicle's logical position within the whole road network. And then the goal selector will use these data to generate a set of motion goals I've mentioned before. So the first step is to generate the current action needed to be taken. That's they call it current goal. And also there are maximum 3 other specific actions could be taken in the future will also be generated. So here we have the transition goal, which is the action the vehicle intends to take right after the current goal. And if we are approaching or moving through an intersection, the system will generate a next intersection goal. Similarly, if we drive into a parking zone, so the system will give us a pre-planning goal so that we can reduce the planning delay, planning latency in the parking lot. And in the intersection handling part, the most important observed here is precedence estimator, and we also have the transition manager. So here you can see in the precedence estimator, it actually determines whether and when it is safe for the vehicle to proceed through an intersection. And the output of the precedence estimator are 2 Boolean subjects, precedence and clearance. So for the transition manager, it will first take the output from goal selector. So in this case, in the intersection handling scenario, this motion goal would be the next intersection goal. And also it should wait for both precedence and clearance, those 2 Boolean subjects, to be true. So until then, it can transfer this message to the motion planning subsystem. So yeah, as you may realize that the key issue is really the algorithm behind the precedence estimator. So that means you know that means how you can tell whether the precedence and the clearance, these two subjects, are true or false, right? So let's first take a look at the precedence. The precedence subject is defined as they said whether it is the vehicle's turn among the vehicles waiting at stop lines. So here, the novel thing is they decided to assign the precedence to individual stop line rather than directly to the specific vehicles. So the reason they do that because it will reduce the error from sensing and tracking obstacles, tracking vehicles. Because if you use the stop lines are always there. They will not move. So this is the major advantage. And then they use a geometric notion of occupancy to determine the arrival time. So here you can see actually the system will compute occupancy polygon. So if any front bumper of a moving obstacle is inside this polygon, then it is considered as occupied. It is considered as an occupied polygon. So based on the yield to right rules, they also assign a bias function for the calculated arrival time. So the stop line that are to the right will receive a negative bias, and the stop line that are to the left would receive a positive bias. And the precedence ordering of multiple vehicles at an intersection could be represented by by just sorting those bias the arrival time in ascending order from smallest to largest, because the to the right are negative, right? So actually, you can imagine that this occupied polygon list is kind of it's kind of dynamic. It's changing from time to time. So only when the target stop line for boss come to the front of that occupied polygon list, will the precedence subject become will the precedence subject have the true value. So and then the next thing is the next subject is the clearance subject. So we need to think about whether the intersection is clear of vehicles and whether there is sufficient opportunity for us to safely cross or merge into any relevant lanes of moving traffic. So here they also use the occupancy polygon method, and they will construct at least one. But in this case, regarding this T intersection, they construct two occupancy polygons over the interior of the T intersection, and one, as you can see, one is the yield across polygon, and another one is the yield inter polygon. So we can also calculate the length of the polygon by this formula. You can see the Vmax is the speed limit for this intersection lane, and T action is the time we need to complete the maneuver into the intersection. T delay is the compensation for the system delay, and T spacing is the desired temporal spacing between the vehicles. And also we have a configurable safety margin, D safety. So yeah, actually the logic here is the same as used for the stop line. So that is, if there is a vehicle, there is front bumper of vehicle detected inside the polygon, then the state of this occupancy polygon will turn into occupied. And at this time, the value of clearance subject become false. So that means the lane, the intersection is not clear, and we cannot maneuver into it. So to make sure that the lane is clear, we also need to calculate yield window, which is nothing other than the minimum estimated arrival time among all vehicles approaching this intersection. So for any moving obstacles, the estimated arrival time is simply calculated by dividing the distance to the crash point. Here you can see there is a D crash point, divided the D crash points by the vehicle velocity. And only when the minimum estimated arrival time is larger than the sum of the T action, T delay, and T spacing. So only when this time happens, then will the yield window considered to be constantly open, and the clearance subject, the value of clearance subject will be true. So this is kind of the logic behind the precedence estimator. This is how we determine whether the clearance and the precedence, these two subjects, are true or false. So cool. Now let's move on to the last racing vehicle, which is Junior from Stanford. And in the previous two sectors, we've discussed a lot of subsystem into the a lot of subsystems of Talos and the bus. We've discussed about the lane and obstacle detection and tracking. We've discussed about the motion planning algorithm. Also talk about the behavior executives in certain situation, especially in the intersection. So now in this sector, I would like to focus on another important task, which is localization mapping. So first, let's just go through the overall software architecture of Junior. And as you can see, there are roughly 5 modules. We have the sensor interface, we have a perception module, we have navigation module, user interface, as well as the vehicle interface. So, from the overall framework, I can tell it's quite similar with the previous two we've talked about with the Talos and Boss. So we have the sensor interface, we have multiple sensors, and then under the perception module, we have the localization subsystem kind of tells where are we in a precise manner, and we have the static and dynamic obstacle tracker, tell us what's the environment look like around us, and then in the navigation module, it consists of a number of motion planner, which give us the answer of where is our next target and how we can get there. And we'll send this information to the steering control and the throttle and brake control to realize these maneuver, these actions. So cool. First, let's just take a look at the sensor configuration. I would say it's also quite similar with the previous two. You can see the Velodyne 64 3D LiDAR mounted on the top of the vehicle, and it's the primary sensor for the obstacle detection, while the other planar LiDARs, the EVO, the SICK LiDAR, the Regal, are used to supplement the Velodyne data because due to the geometry and mounting location, there is a blind spot around the vehicle in Velodyne's data, so it cannot detect the curve of those small obstacles near the vehicles. So, but the planar LiDAR can exactly detect those obstacles in the near range. All right, then I would like to spend some time on mapping and the localization. But before I dive into the detail how Team Stanford achieved the high level achieved this high precision localization for Junior, I think it's worth taking some time just walk through the basic idea and general process of a very important concept, I think, which is called SLAM. And you can see the SLAM is the abbreviation of the simultaneous localization and mapping. So there are two things we need to accomplish in SLAM. So first, we need to construct a map of the unknown environment, that's mapping, and then at the same time, we need to keep track of the robot's location relative to that map. So that's the localization, and we need to do these two things at the same time so that we can really know where are we in the map. And actually, this is not a very new idea. It's a quite classic, quite old concept, and it was applied. It was applied a lot in robotic industry, both indoor robots and outdoor robots. But yeah, the essentially the self-driving car could also be regarded as a robotic, right? And SLAM is also widely applied in underwater systems and airborne systems. So yeah, typical method to solve the SLAM problem is the common filter and particle filter. So yeah, on the right hand side you can see a common filter illustration. So it uses the position measurements and the sensory information from the sensor, especially those planar LiDAR, I believe, to generate a Gaussian distribution of the possible position of the robots. So that's the basic idea of the common filter. Now what I want to show you next is the basic process of SLAM based on extended common filter algorithm. Actually, this EKF algorithm is not used quite frequently today, but as one of the first probabilistic SLAM algorithm, it still has great explanatory value, I think. So you can see here the blue circle represents the robot, and the star represents the landmark. And so initially the robot used the laser scan, use the laser scanner to measure the location of those landmarks. So you can see these lightnings represents the sensor measurements. And then the robot moves. It moves to the new position, moves to the new location, and the distance moved is given by the robot's odometry. So then the robot once again measure these landmarks, and so it has three new observations, right? But after these two observations were associated and compared, so the robot actually found out that, wait a moment, there is something wrong, and these new observations don't match with where the robot thinks they should be, given the robot's current location. So thus, so the robot actually is not where it thinks it is, right? And the robot is also kind of clever. It knows that the sensor is more accurate, so the robot believes more its sensor than its odometry. So it decides to use the information gained about where the landmarks actually are to determine where it is. So now the robot knows that he needs to update the information about the odometry. So actually, this is it knows that this is its current location, right? It's this dash circle. But however, in actual fact, that the robot is even not here. The robot is here in this dotted circle because the sensors are not perfect, right? The robot will not precisely know where it is. However, you can see of these three circles that this estimator with the sensors is better than relying purely on odometer, right? So that's the idea of the SLAM. You need to kind of constantly localize yourself, constantly update the odometry, constantly correct the relative position in terms of the map. So now we go back to the urban challenge. We know that in the urban challenge, the map file was the RNDF file, and it contains all of the digital map information of the urban road network, and is specified in GPS coordinates. So there is also an onboard inertia navigation system (INS), which is this planning system. So but the problem is that if the vehicle just blindly follow the road using RNDF and Planix post estimates, then the error will be huge. So the vehicle would frequently cross the center line or even hit a curb. So what we need to do is we need to also do the precise localization using our sensors. So here they use the local sensors, especially those planar lidars, to provide two type of information to kind of do the correction. So the, the first information they use is the road reflectivity, and the second information they use is the curb-like obstacles. So these two informations can help them do the estimate the local alignment between the RNDF and the vehicle's current position. So basically, that means that the junior is continuously, the junior continuously localize itself relative to the given RNDF map. So you can see on the picture that here the red bar shows the localization results just using the Planning system, and the green curve is the likely location of the landmarks provided by the laser scanners, and the yellow curve is the posterior distribution in the lateral direction after we using the laser scanner to do the precise localization. So you can see on the right hand side chart that actually in the real race, so most of the case, the lateral correction is not that large, but at times the lateral correction will be over 1 meter or even 1.2 meter. So that could happen. Yes, good, good. All right, we're almost to the end, and I would like to sum up a little bit. There are some similarities among all these three racing vehicles in terms of their system architecture. So first of all, they all have these three fundamental parts, which are sensing, perception, and planning. As you can see, in terms of sensing, they were all equipped with the multiple sensors. Uh, these sensors are partially fused or partially redundant, and or also with specialized functions. And I think the real highlight is that it was the first appearance of 3D lidar applied in autonomous vehicles. And regarding the perception subsystem, all these three teams have quite the same understanding that the perception actually serves as a very important platform to connect the other parts, because it takes the data from sensors and then use the algorithm to do the sensor fusion, or you call it data fusion, and then transfer this data and use other algorithm to solve some of the question, like how to do the obstacle detection and checking, and how to do the lane detection and checking. So these questions, I think, are very important for us to for the vehicles to move forward. And last but not least, in the planning subsystem. All of them are considering combining the high level mission planning with the low level motion planning. And really, at the end of the day, what we want is to find a feasible path, right? We want to find a path with which the vehicle can drive safely and efficiently to reach a target, to reach the goal. Yeah, of course, there are lots of novel features and specialized technologies coming from each team and each vehicle. I would say for BOS and CMU, their behavior module is really an interesting sector. It's more specific compared to the traditional planning system, just with motion planning and mission planning. I think this system architecture is really more robust to handle those situations. For example, the intersection handling, right? It's in case of some uncertainty and unpredictable, dynamically changing environment, you need this kind of robustness to make sure that you can handle this kind of situation. And for Junior, we've talked about its localization methods, and yeah, it's used the road's reflectivity and curb-like obstacles, and also the measurements from the planar lidar to do the precise localization. And I believe actually, I think the guy who was responsible for this part in the team, Jesse Levinson, he is he joins the start autonomous vehicle startup called Zoox, and he really did a great job regarding the precise localization. And actually, I also read one of his thesis. It's about how to combine the 3D lidar to into this localization process to remove the potentially dynamic objects and to just keep the information of flat road surface. So I think it's kind of it's a kind of it's this kind of method is will provide more precise localization results than they use in the DARPA challenge. And for Talos, it has a unified planning and control architecture. So actually, I mentioned before, it's a closed loop system, so which is also more stable and more robust. All right, so here's some thesis and researches I took as reference when I prepared this webinar. So if you have more interest in those technical details of these systems, yeah, just Google the name of the articles, and I think most of them are public now, so you can just dive deep as you want. Yeah, it's really cool to see the detailed explanation of those technologies. Yeah, that's it. That's really all I got in terms of the 2007 DARPA Urban Challenge. And yeah, what I found really fascinating is that the DARPA Grand Challenge from 2004 to 2005 and to DARPA 2007 Urban Challenge, you know, it's really more than a game, more than a race. There are a lot of amazing researches and novel technologies coming out from these events, and there are also a lot of talented, amazing people. Walk out from the campus, from those teams, and they step into this emerging self-driving car industry. They go to the company like Google, Auto, Uber, Zoox, Nutonomy, and Faraday Future. So there are also a lot of companies, especially those startups. They are looking for people who had this kind of experience, who was the first bunch of guys dealing with the self-driving car. So in this sense, you can really understand that the impact of these three events is huge. And because 10 years later, self-driving car becomes one of the buzzwords people are talking about. I mean, if you it's you can really see that uh, it's the whole industry is evolving in such a fast pace. You can hardly imagine that each player in this industry, from those incumbent OEM such as Ford, Daimler, and to those tech companies, Google, Tesla, Uber, and also a lot of the startups, they just pushing the whole industry moving forward so hard. So I'm really interested in this industry, and I think self-driving car will become the very important technology. It will totally change our life. And yeah, by the way, in terms of the self-driving racing vehicles, I think there is a robo race, which is self-driving electric car competition. It will come to come to do come out next year, and it will be the prior race for the Formula E in the next season. So I think this season they will do some tests, and they also launched a documentary video on YouTube about how they bring together this self-driving racing car and how they test it. So yeah, if you haven't seen it, just search Rubber Race in YouTube, and you definitely want to check it out. It's super cool. I'm super excited about this race. And I just can't wait to see uh, how this 1 hour competition will be like in the next year. So without human driver, purely depends on the software algorithm, and the is AI replacing the drivers. All right, it would be so cool. I can imagine that. So again, thank you everyone for joining and watching this webinar. And I also would like to thank for all of you who gave me a lot of support during my preparation for this presentation. Yeah, especially my girlfriend. I know she doesn't feel as excited as me about self-driving car, but um, she really gave me a lot of motivation and encouraged me to do whatever I'm interested in. I I really appreciate this opportunity to share with you guys some of my recent work and research. And yeah, if you find any mistake in my presentation, or you just want to discuss something with me, just feel free to contact me. You can message me on Facebook, Twitter, or WeChat if you're from China. Also, you can contact me with email. So any feedback, positive, negative, any suggestion, any thoughts for the further webinar is appreciated. So I think later I will also put the slides maybe on the slide share or somewhere else where you can access to. So thank you again for spending time on my presentation, and it's really a fantastic learning experience, I think. Yeah, I no, I it's really, I would say it's really harder and tougher than I imagine. It's more time consuming. I spend a lot of time and effort on it. Although I'm also stuck with some group work and project from school, but I really enjoy this process. It's really a unique learning experience, and hopefully you guys also learn something from my presentation, and yeah, that would be better. So thank you very much. Thank you everyone, and have a good night.